Hello and welcome to Season 2 of the Oxford Online Maths Club. It's very exciting. I'm joined today by Dr. Vicky Neale.
Hello, I'm very excited too.
I've created a sort of echo effect by playing Season 2 on my laptop at the same time. That's exciting, isn't it? What a great start to the season. It's fantastic to have you with us, Vicky. We're going to talk about some number theory, but I've got some admin at the start to do first. If you're just joining us today for the first time, then it's great to have you here. We're going to have a lot of fun doing some number theory. I've got a poll over in Slido. So Slido is the thing on the screen underneath us here. We're using it as live chat. It says Q&A on the screen, but we're also using it as a chat feature to talk about things. Right now it's running a poll to see if there's anyone new here. There's at least one person who's new live on the Maths Club and who's found the Slido. Fantastic. We're joined in the Slido by two of our current students. Their names are Zakai and Lauren. They're going to be hanging out in the chat to answer your questions, either about the maths that we're doing on stream, or if you want to talk to them about anything else, then they're there and you can chat to them. I'm in the chat as well, and I think Vicky's got the chat somewhere, maybe.
Yeah, I think somewhere maybe is a very good description.
Fantastic. Okay, votes at the moment. People are voting. Seems we've got a lot of the regular people here who've been to almost every episode live. That's winning the vote. But at least a few people who have found out about this recently, perhaps in between Season 1 and Season 2. All of Season 1 is available to watch back on the Maths Club website. If you've somehow found this without finding the Maths Club website, I don't really know how you did that. We're over at maths.ox.ac.uk/r/club if you want to watch previous episodes and further reading related to previous episodes. So that's all over there. Every episode also comes with some further reading afterwards. So on the day after the live stream, I post a kind of blog post of bits of maths that you might be interested in related to the live stream. So if you check back on the weekend on that website, there'll be some related reading. And in between seasons, I want to do one bit of promotion for some content. We did some not live recorded videos. One was a wrap up of things from Season 1. I did the thing people in chat were asking for, where I got back some of the guests from Season 1. Not quite all of them, but I got back some of the guests from Season 1, and we had a chat about Season 1. And I also got Deepak back on the channel to do some more curve sketching. So those videos are kind of bonus content in between Season 1 and Season 2. But that's a sort of bonus extra thing. Okay, fantastic. Right, how's that poll going? That poll's going pretty well. I think people who have been here before have won the vote, so that's nice to see. Right, okay. I think that's my admin out of the way at the start. It's great to have everyone with us. I think I've said all the things I'm supposed to say, and I've remembered to turn on sound, which is usually the thing I get wrong. Which I think means, after all of that I can turn on your slides. So there we go. And I'm going to hand over now to Vicky for Picture This. Thanks, Vicky.
Thanks, James. Thanks for inviting me on. It's really great to be joining everyone now. So yeah, the plan is we're going to work on some number theory, and I hope that you're going to join in. And I'm not sure that I have enough eyes to be able to see the chat and everything else going on, but James will tell me exciting things that you're suggesting. Before we dive in, I just wanted to say one thing about the spirit in which I hope you'll approach this. Oh, and good, the cat's come to help already. That's a great start. Which is, I guess sometimes when we do maths, maybe somebody introduces a piece of maths and then gets us to practice it or something. And that can be a really good way of doing things. And that's not what today is about. Today is, I hope, more of a kind of journey to you discovering some maths over the course of it. And I hope that you will approach that in the spirit of enjoying the journey rather than trying to guess where we're going. You know, imagine we've all just got on a train somewhere and we know we're going a really long way on the train, but if you spend the whole journey thinking, oh, I wonder whether this train goes to Edinburgh, it's not going to be nearly as much fun as if you just look out the window and see what you can see. So we are going somewhere exciting, but don't try to guess where we're going, just see what you notice along the way. So I hope that kind of makes sense. And there probably won't be too many more irrelevant train metaphors as we go through. I want to show you some pictures, hence picture this. And I don't want to tell you very much about them because I kind of want to see what you notice. So I've got a few of them. Let me show you the first one. So here's a picture corresponding to two numbers, which you can see at the top there. So this is the diagram corresponding to the numbers 197 and 113. And I sort of don't want to tell you anything at all about the diagram, except I will tell you one thing as a concession to the technology, because I know sometimes things get slightly distorted with, computer slides and everything. If something looks like a square, it's meant to be a square. So I will tell you that much. And really, I just want you to see what you notice. And I've got 4 of these diagrams to show you with different pairs of numbers. So let me show you another one. So here's the diagram for 123 and 51. I'll just give you a bit of time to see what you notice. Maybe think about what the diagrams have in common, what's the same between diagrams. Maybe think about what's different between diagrams. Let's have another one. Here's a diagram for 25 and 75. I can go back and cycle through all of these again. So if you suddenly think, oh, I can't quite remember about the first one, I'll go back to it in a sec. And there's the 4th one. I had to zoom this one massively because the tiny squares are so tiny. I mean, I sort of hope you can see them there. So this is a diagram for 196 and 151. So yeah, really, I'm just interested in, what do you see? What do you notice? What do they have in common? What are the differences between them? So let me whiz back to the first one, and I'll just go through those again. And I'm hoping that some of you are typing interesting things in the chat, and James can kind of share some of those with us in a moment, maybe.
So far we have, Raphael has suggested that this whole thing looks Fibonacci, with Fibonacci being an adjective. So some sort of relation to Fibonacci, who's a person, but has some maths. So I can sort of guess which maths Raphael might be thinking of.
There's a third diagram for you.
Phoebe says, are we making shapes with the numbers dimensions, but only out of squares?
Interesting.
So some idea about the relationship between the shapes and the dimensions. Somebody says 75 over 23, says an anonymous user. 75 over 25 is 3, and there were 3 squares. Is that a coincidence or a correlation?
I don't believe in coincidences in maths.
Oh, okay.
I just sort of fundamentally don't. If you see something interesting going on, there must be something, right? I just don't believe in coincidences in maths.
Molly says that some of them look like they might have the golden ratio.
Interesting. Shall I go through them again while you're reading some more of these?
Yeah, yes, please. So has this one got some... I can see on my screen, because I'm broadcasting this, there's some really tiny squares. Could you point at the tiniest squares so we get an impression of...
This one?
Yeah, there's some how many? Is that 2 tiny squares?
There's 2 tiny squares here, and then there's one little sort of next size up above it. And then there are these, I don't know how many of these there are. 1, 2, 3, 4, 5, 6, 7, 8. This is my counting skills of these dark orange ones. They are very tiny.
Matt suggests that the length of the whole rectangle is the bigger number, and the length of the squares is the shorter value. I guess maybe Matt means the length of the... Well, there's lots of different squares, aren't there? But maybe the length of the biggest square. And there's a couple of suggestions of some sort of algorithm, but I don't know what to make of that, really. I can't see an algorithm. I can see squares.
Yeah, I see loads of squares, and yeah, shapes, and it's interesting kind of trying to think, how do the numbers relate to those diagrams? So it's great people have got some ideas there. This one has really, really tiny squares, right? This is the tiniest one. So I think there are 3 microscopic squares here.
The squares seem to...
And then
I don't know if you want observations from me, but the squares seem to get small very quickly. There's a huge square right next to those, right?
Yeah, there is a huge square, but I mean, not always, right? I mean, this one doesn't have any very tiny squares.
Somebody says it looks a bit like the proof of the chain rule, and I think they've remembered my episode about the chain rule, where I also had some rectangles drawn around. That's nice. I'm going to assume they're remembering my content rather than learning from anyone else's content. Flynn's got a suggestion that I think is really interesting, to say if you put 1 and phi as the inputs, then you get something or other. And Flynn's got a claim about what happens.
Interesting. Yeah, so I think these kind of conjectures, these predictions about what's going on, I think is really great. I think that's what we do as mathematicians, isn't it? We see something and we try to make sense of it and try to kind of make predictions.
An anonymous person has confirmed that it was my content they were thinking of. The anonymous people, I tend to assume that they're all the same person, so that all makes sense to me.
That's totally how that works, isn't it?
Visa would like to know if the colour of the squares has significance.
Yeah, that's a great question, and the answer is no, not really. It's there to help distinguish between the different sizes of square. So squares that are the same colour are the same size, and squares that are different colours are different sizes. But precisely what the colour is doesn't matter too much, which is a relief, because probably by the time it's been through my laptop and whatever James's computer system is doing and all the rest of it, you're seeing a different colour from what I'm seeing anyway, but it doesn't matter.
I think it helps you see the squares that are different sizes, right?
Yeah. Also, it's quite nice having different colours, maybe. But,
do the yellow-orange squares count? Yes, they do.
They do count. Yeah. Please don't discriminate against squares just because they're orange. They're still squares. So maybe I've got 2 questions. Shall I ask my 2 questions? Is that a good time to do it? Let's do that. So my 2 questions for you are: if I give you a pair of numbers, can you draw the diagram? And the other way around, if I give you a diagram, can you work out what the pair of numbers were? So sort of 2 questions there, both ways of this process of what's going on. So if I give you numbers, can you draw the diagram? If I give you a diagram, can you figure out the numbers? So I think maybe I just want to sort of give you a bit of time to think about that. I'll go back and show you the pictures again in a moment so that you can keep looking at those and thinking, okay, if I have those numbers, how would I have come up with that diagram? Those kind of things. So I'll show you those again, have a bit of a think, and maybe in a couple of minutes or something, I will give you a pair of numbers and you can have a go at drawing the diagram. Probably not drawing it on Slido, because I'm not sure that Slido has a brilliant draw maths diagrams button, but we can experiment. We can see how creative you are at describing your diagrams on Slido. But let's just have a look, have a think about the diagrams in that context. If I give you numbers, can you draw the diagram? If I give you the diagram, can you find the numbers? Not draw the numbers, which is what I was about to say. So I hope that's clear, and I'm sure James will tell me if anybody says that they're not quite sure when I'm asking those kind of things.
I'm keeping an eye on chat. Mostly people are suggesting what might be going on with the pictures. So I've seen people talking about ratios, people talking about dividing, in the sense that the 75-25 example, where we suggested maybe it's not a coincidence that 75 is a multiple of 25.
I sort of feel obliged pedantically to point out that it's a 25 and 75, not a 75 and 25.
Ooh.
Whether that matters is a matter for discussion, but literally what I'm seeing on the screen in front of me says 25 and 75.
Fair point. 25 divided by 75 is not 3.
True.
Big numbers make so the big numbers make dimensions of the rectangle. So I suppose there's a question. I like it when people are putting questions in the chat as well, so that even though you asked some questions, people are asking questions back, right? So
that's great. I love that.
Charlie asks, do the big numbers make the dimensions of the rectangle? So
I think that's a great question, and I conjecture that Charlie's question is really a conjecture phrased as a question. I think Charlie thinks that is what's happening, and it's a great conjecture, and I'm not going to comment on whether it works or not, because you can keep playing and experiment, and all will become clear later on, maybe when you have a go at making a prediction for a particular pair of numbers and we test it out. Asking questions and making predictions is great. Shall I show you another diagram for a bit?
So, yeah, I think because of slight stream lag, people are now suggesting ways they might not understand. Sorry, from when that got mentioned a minute ago. Somebody says the problem seems a bit too random. That there's sort of, maybe there's, is it possible there's no relationship between the numbers and the squares, Vicky?
I guess it is possible, but I'm telling you there is a relationship.
Okay.
And yeah, they're quite open-ended questions, I guess, in a way. It's not like do this calculation or something. It's a little bit vague, but hopefully that gives you scope to kind of find something interesting to think about in there. So those were the questions that reminds people.
I suppose it's slightly frustrating, perhaps, that you've got 4 examples and an idea of what's going on, and
yeah, I realise that this is a kind of new thing, and I'm asking people to figure it out and not giving you loads and loads of data. Like 4 examples is not loads.
Hi, Zach. Zach's just got back from school, jumped in the Slido, said hi.
That's cool.
So, yeah, are we supposed to find out the relationship between the two numbers and the figure? Question mark, exclamation mark, which is like a question and a statement, right? And yes, that's I think what we're looking for. A relationship between numbers at the top and the picture that you get out. Given the numbers, can you make the picture? And given the picture, can you make the numbers?
Exactly, yeah. So in a moment when it seems like we're ready, I don't quite know when that will be, I will give you a pair of numbers and invite you to have a go at drawing the diagram, and then I will show you the diagram that my computer produced when I gave it those numbers, and you can kind of compare notes. And then I'll show you a diagram without the numbers and ask whether you can figure out which numbers led to that diagram. So we'll kind of test it out both ways around.
And there's a request for keep switching between the diagrams if we
Thank
can.
It's very hard to know how long people want to look at diagrams for, but I will try to keep mixing it up. So yeah, so let me see whether I can pick out some of the things that have been said so far. So we've talked about maybe chopping up a rectangle into squares. I think that was kind of an idea that came up. Something significant here about the fact that 75 divided by 25 is 3. Ideas about maybe the numbers relate to the dimensions of the large outside rectangle in some way. Or maybe the larger number is the long side of the rectangle and the shorter number is the side of the largest square. Some of those kind of things coming through, I think. I love that James has arranged a soundtrack of birdsong. I think this is great.
I'm surprised you can hear the bird song. The birds are outside and the microphone is inside. Even if it sounds like the other way around. So Sebastian's got a request. Can you please show the length of the smallest square? Is that something that you're offering? I'm not sure.
Nope.
Not sure that it is. No.
That is not on offer at this point, I'm afraid. So, yeah, make of that what you will.
People would like a hint in the form.
I will tell you how many squares there are, because these diagrams are pretty small. I realise, like, even on my laptop screen, they're pretty small. So I'll tell you how many there are, if that helps. So here I've got 2 of the smallest size, and then 1 of the next size up, and then 8 orange ones, and then I think there's 1 here, and then probably they're big enough that hopefully those show up okay. This one, they're a bit bigger, which is a relief for my eyesight. So there's 3 of the smallest, 2 of the next size up, and then 2 and 2.
So it's an anonymous person just got highlighted a little bit, or repeatedly find remainders is a suggestion. I don't know. I think I can sort of imagine how that might work as a kind of pattern of working out a picture or something, but I haven't tried it.
Just on my counting squares here, public service, I think there are 3 of the tiniest ones here, and then 4 of the next size up, and then 1 and 2 and 3, and then 1 of the biggest ones.
Right, okay.
Can we have a bit of feedback? Are people ready to give this a go if I give you a pair of numbers? So I want to reassure you, there are no consequences here at all, right? So if I give you a pair of numbers and you draw a diagram that looks nothing like mine, it's fine. It's not a problem. So we could just give it a go. Should we give it a go, James?
Yeah, let's give it a go. I think some of them, I've been cunningly not reading out answers that I think
some people might be further ahead than others.
Some people might have got a very accurate impression of how to make the pictures that they've seen so far.
Okay, well let's give this a go.
We can always try.
So can you draw the diagram for the numbers 127 and 105? And I'm assuming that you're going to draw this on a piece of paper or whatever it is that you've got there, and then creatively describe as best you can something on Slido, or just tell us you've done it, or whatever you like.
They can tell us about the squares, right? They could
have
some descriptions of squares. Yeah, Slido doesn't have a feature at the moment to, could give everyone a little whiteboard that they could draw things and submit them, and maybe it shouldn't have this feature. Okay, 120. I'm going to have a go as well. Oh
yeah, that's a good plan. Yeah.
Immediately on seeing these numbers, I've wished that I was paying more attention to which way round certain examples were in the previous examples. Somebody's highlighted a comment saying I'm good at drawing, so I'm now obliged to have a go.
Aha. Okay, great. Let's see what James comes up with.
Oh goodness, which way round was it? Right, okay. So I've drawn one square, so I can't be wrong, right? Everything you've shown me so far involves some squares. What do I want? I think I've also drawn a rectangle, so I'm probably wrong now. But people are now putting numbers in the chat, and I don't know what the numbers mean. Somebody has posted 14132.
I hope it's not their pin.
Goodness, it's almost the digits of pi. It's not almost the, well, I mean.
You know what I said about there not being coincidences in maths earlier, James?
Oh, great. I think I'm going to approve this message. I think it's disappearing down the chat, but somebody's tried to start drawing a square, I think. Possibly.
Wow.
It's not gone very well. Oh well.
It's quite hard.
The more squares I draw, says Josh, the more rectangular my squares get. I think that's a statement about the golden ratio, isn't it?
That is precisely my experience when I try to do this, Josh. That is exactly what happens.
Yeah, I've realised I've got a kind of quite squarish rectangle, and realised that I want about 5 squares in it, and I don't know what I'm doing next. Oh yes, I do. No, I've drawn way too many squares. Okay, that's a rectangle. Can I share what I'm drawing? I don't really want to give it away though, in case.
Well, I'm going to give it away in a minute because.
Oh, okay. Chat, I've drawn the following. Let's hold it up to the camera. I'm not done.
This microscopic picture of James on my computer, which is like even smaller than squares.
I've drawn one big square, and I've put 105 at the top. I've put 105 down the side. And then at the bottom I've worked out, because I want the height to be 127, I've got a little rectangle at the bottom that's 22. Ooh. And then I haven't really worked out what to do with that rectangle. But all I wanted was, I wanted the big rectangle to be those numbers, and I wanted at least one square. Thanks for coming on my live stream and looking at my drawings, Vicky.
Happy to oblige.
How would a multiple choice answer work for this? Options, I've got lots of squares, I've got some squares, or I've got not squares. How
are people getting on with their diagrams? Do you want a bit more time? Do you want me to show you a diagram on my computer? What do you think?
A couple of people have posted numbers of squares.
Interesting.
Right, okay, we're doing... Hang on. I'm just gonna do some interaction.
Okay. I'll wait for James to interact. Well, that's what James is doing already.
Oh. I've done a poll. Do you want the answer now? Are they ready for the answer?
Okay, I think there's a... Ooh. I thought it was clear. And
the people who are ready, the people who've already done it, are hanging out in Slido, telling us about numbers, and they're ready to click polls. You know, got to give them a minute. Possibly our best chat message is an anonymous person who says, "So far, I've drawn a square," which is...
That's great.
Number of squares? That would require me to know how many squares there are supposed to be. And as discussed, I've got 5 so far, and then an item that looks squarish, but it's probably not square. So I've got 4 little squares along the bottom.
I think I should show what I've got on my computer. Okay.
Yeah, that's a good idea.
You do that. Take the pressure off your square drawing a bit. Okay, here's what my computer got. Pause for people to digest. See whether they got something similar.
Oh wow, people have actually posted. Wow, at some point while I wasn't looking underneath the poll, people have adopted like quite a consistent notation.
Wow.
It's like watching something evolve. Or
that's such a mathematical thing to do, to like invent what is the right notation for doing this and Slido. That's great.
Yeah, like look at... So it's just disappeared off the live stream. If you scroll back, Sebastian and King Richard IV have put basically the same thing.
Cool.
I should have warned you.
It seems to match up to the diagram on my computer screen in a way that we all understand.
Let's read Phoebe's. 1 massive square, 4 smaller, 1 smaller, 2 smaller, 2 smaller, 3 smallest. Maybe a 3 in there. 1, 4,
I think I've got
1.
a 3 and a 2 the other way around from you, Phoebe. Because I think my smallest ones, there are 2. And there are 2 of the next orange one. And there are the 3 lightest blue here.
So the person who said 1, 4, 1, 1, 4, 1, 3, 2, 2?
Yeah, I think I can match those numbers to my diagram. That sounds great.
I was looking at your diagram when I said that.
Oh, so, okay. Then it's not such a surprise it matches.
Flynn, so people have been doing some subtraction in chat, and we've discovered that a challenge of drawing squares, and there's also a challenge of doing subtraction.
Okay, yeah, this does involve doing some arithmetic. Yeah, that's definitely important with this.
Flynn has bravely suggested a subtraction style. Anyway, right. Okay, yours is the other way around to mine. And mine's not even done. So I'm wrong.
So I think when I think about trying to draw this diagram, I start by drawing a rectangle. I think this is what you were doing. And I guess I'm putting the first number across the top and the second number is like the height of my rectangle. And then I think I'm thinking about this as chopping off as many squares as I can of the largest size that will fit, starting at one end. So that will be the side length of the smaller number. That's, I think, what you were doing with your 105 by 105 square, James, wasn't it? So we chop off as many of those as we can, which turns out to be 1. And then, as you said, that leaves us kind of 22 by 105 rectangle. Now I'm trying to do subtraction in my head on a live stream with a cat shouting at me in the background. You're really not helping, cat. So now I've got a 22 by 105 rectangle. And now I kind of think of just doing the same thing again, as though I'd started with the numbers 22 and 105. So I chop off as many squares I can of the biggest size I can. So that gives me my 4 22 by 22 squares. And then I've got this little one left, whatever it is. And then I kind of just keep going. So in my head, there's only one thing I do, which is draw a rectangle, chop off as many of the largest squares as I can. And then I just keep doing that because then I've created some smaller rectangle and I can just kind of keep doing the same process again. I'm curious about whether that relates to what anybody was doing, whether that's how you were thinking about it, whether anybody was thinking about it differently.
I saw people earlier talking about ratios and finding, like, doing division and working numbers out.
Yeah, interesting. So I'll show you a little bit later on that we can think about it. I guess the way I described it just now feels to me quite geometrical, although I have to do a calculation to work out how big the rectangles are. But yeah, I could, for example, with the 105 and 22 rectangle, I could do 105 divided by 22. And I guess that's going to be 4 remainder something. And the 4 tells me that I've got these 4 squares. And then the remainder tells me the size of the side length of the new rectangle I'm coming up with there. So yeah, I'll write that down. I've got on a later slide sort of calculations doing it that way. It's a sort of more numerical equation version rather than the visualization with rectangles and squares, because different people like different ways of thinking about it.
People are very interested in your cat, Vicky.
My cat is very interested in the fact that it's nearly her tea time, but it's not as nearly her tea time as she thinks it is. Oh,
and good question that's just come in. If you're new here, this session is 1 hour long. We do 5 o'clock till 6 o'clock this season. It's sort of after school club. And welcome to the live stream, person who's new. I've highlighted this question below. Oh no, there was a pronouns question, and there was. I'm trying to get Lauren and Zakai to say whether they got the right answer as well. And Raphael, who said earlier that things looked Fibonacci, has got a hypothesis about subtracting Fibonacci numbers. Do you want me to read it out?
Yeah, why not?
If you input 2 consecutive Fibonacci numbers, would you get a sequence like 1, 1, 1, 1, 1?
I think that's a really interesting question.
Okay.
So you can kind of tell that these are images on slides, but there is an update button here. There is an interactive version of this. I'm sort of not telling you where it is online at the moment because I I think if somebody told me at this point, I'd have a temptation to go and type in loads of numbers. And I don't want you to type in lots of numbers right now. I want you to kind of look and think and see and play. But I will tell you where it is later. So you'll be able to go and test out these kind of conjectures and what happens if I put in this number or that number or whatever. You will also discover the limitations of this visualization, which that the computer only takes whole numbers between 1 and 200. Just to kind of dampen any enthusiasm that you're going to type in phi. Because I'm afraid you're not on this particular version. Should we have a look at the other question that I asked? So we talked a little bit about, if I give you the numbers, can you draw the diagram? And it sounds like people have got some good ideas on that. And I hope that even if you didn't draw exactly this diagram, sort of seeing what other people were thinking about, listening to me and James rambling on about how we were thinking about it is maybe helping a bit. So the other question I asked was, if I give you a diagram, can you find the corresponding two numbers? And I guess a good way for us to explore that is for me to give you a diagram and you see whether you can find the numbers. So here is a diagram with the numbers chopped off with my brilliant IT skills. Can you find the numbers? And I hope you can see the diagram okay there. So yeah, just have a bit of thinking time, and that one will be easier to type in Slido, I guess, than it was to try to draw the diagram in Slido. And then it all goes quiet while James is thinking about it as well.
Oh no, I was thinking about something else. Sorry. I should think about this, shouldn't I?
Focus, James.
In a minute, you're going to ask me what the numbers are, and I'll have no idea.
I'm not going to put you on the spot, James, because
okay.
I know that you'll have loads of answers from lots of people on the Slido. So
somebody in Slido has asked, "Can you draw this with parametric equations?" And that's a very distracting thing to. I think I can, but can I talk about that? Tricky. Somebody has even spotted that I'm not paying attention in the Slido, and I know that because I was reading the Slido of them accusing me of looking at the Slido. Right, yes. And Flynn says something about storing things in dictionaries, which was also distracting. Thanks for posting in the Slido, everyone. So current challenge is we've been given some shapes, and we've been asked to work out what numbers Vicky put in at the start. That's 3 tiny squares, isn't it? I'm a bit worried about screen resolution. 3 tiny squares,
and then there's 5 of the next size up. And then 4, and then 1 giant square.
Someone says I'm going to steal their answers, so they're going to sneakily all give me fake answers. I think.
I think 3 numbers. I think we should treat this collaboratively, so there's no.
And there's suggestions about maybe. So Phoebe suggests that numbers might multiply to something. Flynn suggests there might be a ratio of numbers. There's some people suggesting, I suppose, multiple solutions. Is that an acceptable way to answer the question when you're asked to find the numbers? I suppose. Maybe. And also people are being ambiguous about which way around the numbers are, which I appreciate because I got the numbers the wrong way around last time. So 3 tiny ones. And then 5 next to them.
Yep.
I'm going to start thinking out loud. So each of the second smallest is 3 along the side. So that little rectangle is about 15 of the second smallest, plus a small one. So there's like 1 pixel by 16 pixels or something, if a pixel is the smallest one. So now I'm doing well because I've got... No, it's like 3 pixels by 16 pixels. I'm not doing well. Now I'm doing better. And then I've got a 16 pixel wide second biggest square. So I've got to multiply that by 4, 64. Add on the 3 that I had at the bottom for the 3 tiny pixels because they line up. But maybe I should be thinking about that as the size of the rectangle or something. I think I've got about 67 on the top, and then I don't want to work out the other number. Other people have said 67 in chat, and those people are also saying 83.
Ah. Interesting.
Someone says, I have no idea what's going on. If you've just tuned in, you see me rambling over some integers. Well, Vicky looks mildly concerned. Do you want to let them know what your numbers were? Or what the...
So, if you put in 83 and 67, you do indeed get this diagram. So, great job, anybody who came up with 83 and 67. Did anybody have other numbers out of interest, or was it kind of a lot of love for 83 and 67?
If you count 67 and 83, early on, so it's easier once some people have posted, right? But early on, people post other numbers in the 60s and other numbers in the 50s, which make me think that, like me, they've added some numbers up, strangely. And yes, okay. But mostly those two numbers. Oh, somebody else has got. Ah, thank you. Students have dug through and found somebody else suggested maybe 134 and 166.
Interesting.
I think I saw someone say multiples at some point. Hang on,
Well, here's what happens if you do 166 and 134.
You had that prepared on the slide.
This is like the least interesting spot the difference ever, right?
Yeah, okay.
I liked your pixels way of thinking about it, James, because we don't know how small the smallest square is. I know somebody asked earlier on how small is the smallest square, and I sort of didn't tell you. And I guess it makes sense that different pairs of numbers can give the same answer because it kind of depends what units we use, like how big is the smallest square. So James's calculations that he was doing out loud were all kind of based on, so I suppose the smallest one's like 1 by 1, like 1 unit by 1 unit. But if the smallest happened to be 2 units by 2 units, then building up from the smallest outside rectangle, we find 166 and 134.
I think lots of people didn't find my calculations out loud very helpful and would like a recap of what I was doing, or actually they'd like you to explain how do you get from the squares to the numbers.
Okay, I will try to do a recap, and I will try to use my mouse and point if that helps.
Don't say mouse near the cat.
I know. I just regret it. It's not even a mouse; it's a touchpad. And now it's disappeared. There we go. I'm back. Okay. So if I'm looking at the left-hand diagram. If you're trying to find my cursor, here it is. So if we think of the smallest square as 1 by 1, the next square up is going to be a 3 by 3 square because its side length is the same as these 3 1 by 1s. So the next square up is a 3 by 3, and there are 1, 2, 3, 4, 5 of those. So this kind of rectangle here, I don't have very good touchpad skills, sorry. This rectangle here is 3 high and 16 wide. 16 because it's 5 lots of the 3 plus the 1. So that's a 16 by 3 rectangle. And that tells us that the next square up has side length 16, because look, it matches up just nicely here. So that's a 16 by 16 square, and then there are 4 of those. So that's 4 lots of 16 gives 64, plus we had a 3 at the bottom, which is 67. So the shorter side length of this whole rectangle is 67, which is excitingly one of the numbers at the top. And what about the longer side? Well, we know that this square on the right-hand end is 16 wide, and we know that the giant square is 67 by 67, so the whole thing must be 67 plus 16, which is 83. Did that make any sense, James?
It made sense to me, thank you. I guess we've now confirmed that earlier we were a little bit vague and evil, and we didn't confirm that there was any relationship between the two numbers and the side lengths of the overall rectangle. But I think now we've seen enough examples, we're willing to suggest that that's what's going on here.
Exactly. And if I'm drawing the diagram and I'm starting with the numbers, I start by drawing a rectangle with those side lengths. Like the first number, I guess, is the width, and the second number is the height, if I've got those the right way around. But it doesn't really matter. You just get a kind of reflection of it or something, but rotation of it. But so the numbers correspond to the side lengths of the rectangle, and you can either start with those numbers, draw your giant rectangle, and kind of chop off squares repeatedly, or you could start with your diagram and build up and work out what the dimensions of the rectangle must be. How are we doing on the Slido? What is the kind of level of confusion on the Slido at the moment, James?
Someone says, the light bulb with my head just lit up. Seems simple now, thank you so much. People liked that a lot more than me mumbling numbers. What a surprise. I totally get it now. This is brilliant. There you go.
That's lovely feedback.
That's sort of instant feedback you get from having a Slido running at the same time.
That's great. And I think there's something kind of interesting about the fact that if you start with a pair of numbers, cat, stop it. If you start with a pair of numbers, there's kind of just one diagram. I mean, there's sort of not just one diagram because it depends exactly which order you do the squares, or like the computer spirals, you can do other things, but basically there's one diagram. But if you start with one diagram, there are different possible pairs of numbers you can have. James is saying, is that okay as an answer? But I guess it has to be okay as an answer because it just is. There are going to be infinitely many pairs of numbers that give the same diagram, but I can't show you infinitely many for a number of reasons, one of which is that the computer only takes numbers up to 200 on this particular version. So I had to choose input numbers that would allow that. Okay, so we've got this kind of process for taking numbers and producing a diagram, kind of seeing the relationship between those. I hope people are feeling kind of okay about that process. I mentioned that we can think about it in more of a kind of equation way, and it sounds like some of you were doing that, sort of thinking about it via division. So let me go back to this diagram, which was the really first one. Excuse me, sorry, I'm talking too much. So this is the very first diagram I showed you. So if it looks familiar, that's why. And let me show you how I might capture this diagram with some equations. So the starting numbers 197 and 113. So what some of you I think were talking about doing was kind of division with a remainder. So we could do 197 divided by 113 is 1 remainder 84. And that's what this equation is supposed to capture. And I could have written it as 197 divided by, like over 113 equals 1 plus 84 over 113 or something. But basically, I really like whole numbers. So I just kind of cleared all my denominators. So I've got loads of whole numbers everywhere. And then we've got 113 by 100. Let me try that again. We've got 113 by an 84 rectangle. Those are kind of the new starting numbers. And we can kind of just do the same process again. We could do 113 divided by 84. See how many times it goes, see what the remainder is. And now we've got an 84 by 29 rectangle. It's as though we started the process with 84 and 29, so we can do 84 divided by 29 and have the remainder. The reason I put this on the slides is so that I don't have to try to do the arithmetic in public live. And then we can do 29 divided by 26, and I can do that one. That's 1 remainder 3. And then 26 over 3, so that gives us 8 with a remainder of 2. And then I could do 3 divided by 2, and that's kind of the kind of arithmetic I feel quite comfortable with. And then if I do 2 divided by 1, because we're now down to a 2 by 1 rectangle, that goes exactly with no remainder. So I could have written plus 0 to mean like there's no remainder, but that feels a bit odd, so I've just not written the remainder there. And I reckon this system of 7 equations kind of corresponds to the diagram. And if I put them next to each other, maybe that helps to try to show that. So the numbers in like the first column after the equals sign, if you like, those are the numbers that I think some of you are writing in the Slido to kind of describe your diagram, because those give the number of squares of each size. So like the 8 in this third equation from the bottom, 26 is 8 times 3 plus 2. This 8 is telling us that there are 8 of these orange squares, for example. So somebody pointed out it's quite hard to draw this by hand because like the squares become rectangles after a bit, and that's totally what happens when I do this by hand. It's fine on the computer, it's quite hard to do it by hand. Doing the equations by hand is a bit easier. It's also the kind of equations that computers are really good at doing because it's the same process over and over again. I think the word algorithm came up earlier. It's a process that you just keep repeating. If you're doing it with an equation-based way like this, just one top tip. In my experience, when people go wrong, it's because they just lose sight of which numbers are doing which jobs. So mathematically, in the jargon, multiplication is commutative. It doesn't matter which way around you write it. So I could write 26 is 8 times 3 plus 2, like I've got here. I could write 26 equals 3 times 8 plus 2. That's still true, obviously. But what I want to do is keep track of which numbers are doing which job. So which numbers are counting the numbers of squares and which are about dimensions of rectangles and stuff. So I drew on some arrows. I hope you like my really high budget typesetting here, James. I put a lot of time and effort into this. I've got these kind of colored arrows to try to show where the dimensions of the rectangles are. So I have this rule that when I'm doing these equations, I always kind of write numbers doing the same role in the same order, if that makes sense. I feel like I'm becoming less coherent the more I'm talking here. Should we check in and see whether there are things coming through on the Slido?
Yeah, the Slido, after understanding what was going on, the Slido's been talking about other things that they can do. People are talking about a particular algorithm. I'm currently holding back a chat message that says this is the name of the algorithm in case we want to keep that as a surprise or a secret.
Let's just hold on to that thought for a moment because we haven't quite reached Edinburgh on the train. I think we're sort of somewhere around, I don't know, like the Lake District, Northumberland, that kind of part of the world at the moment. So let's just sit on that thought for a little bit.
Oh, and people are talking about doing this in 3D.
Oh, that's an interesting thought. Yeah.
They're sort of working it out between them, so I'm just sort of going to let them.
That's great. Yeah, please do come on with an answer in 3D via Slido. That sounds like a really interesting thing to explore. One of the things I like about this is that there are lots of questions that we might ask, having kind of got to this stage of, okay, so we've got this process, like, well, what can we do with it, and how can we generalize it? And I think those are really mathematical instincts to have. Can we do it in 3D? Does it have to be with squares? You know, what else can we play with here? One of the things that we might play with, just steering, because I want this train to keep going a little bit. I said I wasn't going to be any more silly train metaphors, didn't I? Sorry, I changed my mind. One of the things I would like to think about, in fact, the thing I would like to think about, is the relationship between the side length of the smallest square and the starting numbers, so the dimensions of the rectangle. So I don't know if anybody has any thoughts, any conjectures they would like to make at this point about relationships between the side length of the smallest square and the side length of the rectangle. You might want to look back at any examples that you were playing with earlier on to gather additional data. Cat, stop it.
There is an idea in the chat, buried a little bit down. I'm not going to read it out because I want other people who didn't post that chat message to think about it. And they are asking a little bit about applications to the real world. What can you do with this repeated subtraction idea?
I think that's a really good question, and we will get there sooner or later.
They're also talking about the cat a lot, Vicky. They're talking about the cats a lot. Like 80% of chat messages are about the cats.
I see. Okay. Well, she's a very nice cat. I have 2 cats, in fact, but the other one won't appear on camera. She's very shy, but she might appear later. You never know. Focusing briefly on the maths in between the cat. Is there anything coming through about? I'm not giving you very much time here.
There's a suggestion that it might be something to do with the highest common factor of the numbers.
Yeah, that seems like a good conjecture. I think if you haven't had kind of so much time to play around with that and come up with that conjecture of yourself, I feel confident that if I gave you 10 minutes, you would come up with that conjecture. I'm just not giving you loads of time. If you want to have a play with the interactivity yourself, you can. There's a URL. I think if you Google enrich, N-R-I-C-H, and picture this, you'll find it, if that's easier than typing in a URL on a slide that you can't click. Sorry. So if you want to play with it later, don't play with it now. Do other things. Think about maths now. But if you want to play with it later, you can. I'll put that up at the end as well. Here's a conjecture then, which it sounds like some of you have come up with, which is great, which is that the side length of the smallest square, so that last non-zero remainder in the kind of equation way of thinking about it, is the highest common factor of the 2 starting numbers. And I think it would be really great if you would like to have a go now at maybe trying to prove that. Can you find a way to show that that must be true? Maybe thinking about the diagram. If you prefer thinking about the equations, I encourage you to think about the diagram. Can you explain why the side length of the smallest square should be the highest common factor of the 2 starting numbers? So maybe kind of we'll have a couple of minutes of thinking time, and James and I can chat amongst ourselves or something while you see what you can come up with. I've got a little nudge that I can share with you in a couple of minutes' time, maybe. And yeah, James can tell me what else is coming through on the Slido or something.
I'm linking people, so you put a link on the screen.
I've
remembered they can't click on the screen.
Yeah,
putting a link in the chat as well.
That's
something about modular arithmetic I saw, and I wasn't sure if I should highlight it or not. I wondered whether there might be some link to. I guess I can't find the comment anymore, but there's some link about. We talked about modular arithmetic a few weeks ago.
That's good. I like modular arithmetic.
Yeah, and there's sort of a similar idea about, I guess, subtracting things and finding remainders. It's like a common thing between them. There's cool. Maybe like a scaling. Raphael says it seems like there might be some sort of scaling of the unit diagram, and I think someone said this back when you had the 2 examples on the spot the difference. So we said there was a scaling going on between the 2 pictures that would, I guess, you could double all the numbers.
Yeah.
I guess that does double the highest common factor because it's a new bit of common factor.
Yeah.
Yeah, lots of remainders. I sort of think so. I've been distracted because I think Flynn said, "Is this the minimum number of squares that you can use to cover a rectangle?"
That's a good question.
It is a good question, isn't it? Because it's quite you can fill up a lot of the rectangle with quite a big square to start off with, but Yeah, okay. I don't know if later on, if you run into I could imagine maybe running into a problem where you paint yourself into a corner and have to use 113 tiny squares or something.
Is this like a greedy algorithm approach to trying to cover square? You like use the biggest square you can, like loads,
Yeah.
and like when I'm packing my bag suitcase or something, and I put the biggest things in first, and then try to fit the little ones in the corner. But maybe that wasn't the best way of doing it. I don't know. I think that sounds like an interesting question to explore. So I give a little nudge on thinking about highest common factors, just because people maybe haven't thought so much about highest common factors in this kind of way before, trying to justify things with highest common factors. And like, what is a highest common factor? So I think that if we want to show that something's the highest common factor of two numbers, like A and B, we have to show two things. I think we have to show that it is a common factor, so it divides both A and B. And we have to show that it's the highest, that any common factor of A and B is less than or equal to the thing we're trying to show is the highest common factor. So I find it quite helpful to separate out these two roles that a highest common factor has. Like, it has to be a common factor and it has to be the highest. And maybe think about trying to show those two things separately. So I'm looking at my clock because people have to go and have their tea soon, and I want to make sure we talk about this, but I also want to give people thinking time. So yeah, we'll have a little bit of thinking time, see what happens on the Slido, and then maybe I will talk you through my thinking, but there are lots of ways of thinking about it, and you can think about it some more, something like that. If that sounds okay with you, James.
Yes, I'm reading Flynn's comment, which one of the students has highlighted for me. All we need to prove is that the sides of the smallest square, being 1, don't have any common factors apart from 1. We already know that doubling the size of the smallest square doubles the sizes of the square. So I think Flynn's thinking about if two numbers have a highest common factor 1, just need to prove that the size of the smallest square does work out to be 1.
Yeah.
And then deal with pairs of numbers with other highest common factors by scaling up. If you can get it right for things that are highest common factor 1, then you can get it right for other pairs of numbers as well.
That sounds like a nice way of thinking about it. Yeah.
I wonder if you do get 1 at the end if you've got numbers. That's the kind of sub question now, right? Like,
well, let me distract you for a minute, James, while everyone's busy thinking about this, because there is another thought here, which is, do we know that we get the smallest square at all? Ooh. I've sort of cheaply made this conjecture that the side length of the smallest square is the highest common factor, but there's some little, I was going to say this little voice in my head, maybe this is what my cat's worried about. Does this process actually guarantee to stop? Is there a smallest square, or could we just be drawing like tinier squares for like ever? And it turns out that we do stop, which is a relief. So there is a smaller square. My conjecture makes sense. There is always a smaller square. But if people are interested, they might like to think about why. How do I confidently know there will be a smaller square? That's like a thing to think about. I think I am not going to give you loads more time for thinking now. And I'll sort of share with you my thinking, but you can keep thinking about it more, and I hope that my telling you my thinking won't spoil you having a go at your thinking. So here's my diagram and the equations again. So I want to show here that the side length of the smallest square is the highest common factor of the two starting numbers. And I'm doing this with a specific diagram and specific equations, even though it feels like to prove something we should do it like generally with algebra or something. But I think we can see the generality in the specific diagram, and I can't draw a general diagram, and doing general equations, the algebra just sort of obscures what's going on a bit. So let's try it this way. So there's two things to do. One is to show, I'm going to focus on the diagram. One is to show that the side length of the smallest square divides the side lengths of the rectangle, that it is a common factor. And the other is to show that any common factor of the side length of the rectangle is less than or equal to that smallest square. So let me do them in that order. And try to stop the cat helping. So, job 1, show that the side length of the smallest square is a common factor. So imagine these are like bathroom tiles or something. So if I've got bathroom tiles the size of the smallest square here, so each of those is just an individual tile, because that exactly divides the next square up, the next square up can be tiled with tiles of that size, side length of the smallest square. Like, it divides exactly. That's why we stopped. That's why it's the smallest square. And then the next size up, we're going to be able to tile exactly, because we could tile the previous two sizes, and those between them make up the side length. So we can tile these dark orange squares exactly using tiles of the size, side length of the smallest square. And then because we can do all of those, we can do the next size up, the lightest blue, because each of these little squares along here we can cover exactly. And so we can do the whole little blue square using that size tile. And then we can do the next size tile, same argument. And then we can do the next size tile, same argument. And then we can do the next size square, same argument. So we can cover all of these squares using these tiles of the side length of the smallest square. Or putting that another way, the side length of the smallest square divides each of the side lengths of these larger squares, including the biggest square. So it divides the smaller of the two numbers, or the second of the two numbers rather. And it also divides the longer side length here of the starting rectangle, because again, it divides each of the squares that make it up. And that shows that the smallest square, the side length of the smallest square, is a common factor of the two numbers. You can do that looking at the equations instead, if you prefer, but I thought I'd show you the picture, since the whole point was we were looking at the pictures. And now I feel I should draw breath and see whether James wants to tell me that people are telling me that what I just said doesn't make sense.
No, it's like proof by induction through squares rather than going through numbers. So inducting on size of square, or inducting on colour or something.
Yeah, because we're doing the same process over and over again when we construct the diagram, somehow we're doing the same process over and over again in the reasoning. That's kind of what's going on there.
Yes. I've been distracted because people have started talking about colleges. I feel like saying on the stream, none of the colleges is best for maths. Please stop asking. They're all great. They have the same maths degree and the same problem sheets. They do the same content. Doesn't matter which college you're at. Sorry.
Back to the maths. Just to finish off, we also need to show that if you take any common factor of the side lengths of the rectangle, that it's less than or equal to the side length of that smallest square. And again, I could think about that using this sort of tiling type strategy. If I've got some tile that divides, that I can tile the large rectangle exactly, it divides the side lengths of the largest rectangle, then I can certainly tile the biggest square. And I must also be able to tile the next square down, because that distance is the kind of remainder. In terms of the equations, if it divides 197 and it divides 113, it must also divide that remainder of 84. So I can tile all of this square using that unknown tile, and then all of the next squares using the unknown tile, and so on, all the way down. So we must be able to tile the smallest square using this unknown tile size. And so in particular, any common factor of the two starting numbers must be less than or equal to the smallest square. In fact, it must divide the side length of the smallest square. And that gives the second part of the highest common factor. That was quite a whistle-stop explanation, but I hope it maybe gives you enough that you can think about it some more if you're interested, or you could go and look it up or something. So as some of you, I think, recognize, this is something called Euclid's algorithm. Here's a picture of Euclid and a picture of Al-Khwarizmi, from whose name we get the word algorithm. I don't believe either of these pictures has anything to do with what these people look like, because the pictures were way more recent than the people. But anyway, so Euclid's algorithm is a process for finding highest common factors. And somebody was asking about practical applications and so on. Euclid's algorithm is really useful because it's really efficient at finding highest common factors. So if you feed it to 10-digit numbers or something, Euclid's algorithm will really quite quickly find the highest common factor. Way more quickly than, for example, finding the prime factorizations of both numbers and comparing those lists, which might be your other strategy for finding highest common factors. And finding highest common factors turns out to be useful in all sorts of number theory problems. So there's a kind of link computationally with Euclid's algorithm. It also ties in, somebody was talking about modular arithmetic, and James, you said you'd done some on the live stream before, so this might have been relevant. You can use Euclid's algorithm to think about finding inverses for numbers, for example, and it links in with all sorts of things. So if you're interested, I encourage you to look up Euclid's algorithm, or it sometimes gets called the Euclidean algorithm. That's the link if you want to play with the interactivity some more. So I hope that's sort of given you something to play with. You can go and experiment some more, go and look up some more. If you're so inclined, you could decide to knit Euclid's algorithm. This was like a really silly idea. I can't quite remember why I decided to do this. It really doesn't work on the camera, but look, here's a giant knitted version of this picture, because actually I don't have a way to end that sentence. So let's move swiftly on. I think that's everything that I wanted to do, James. Are there any final questions coming in, or do you need to do admin stuff now?
But I don't think we've got to the end of working this out in 3D, but I think we'll leave it for another day in terms of how the cubes fit together. Where do
If
the
people
cubes
come
go?
back next week and tell you what they've done in 3D, James, please let me know.
Yeah. People would like the cat to have its tea. So I think I'm going to wrap up if that's all right.
Good plan.
If this was your first time joining us for Oxford Online Maths Club, great to have you with us. We're going to do this every Thursday for this term. This is season 2 of the Maths Club. So join us back live next week for a bit more maths. There's further reading related to this that's going to get posted on the Oxford Online Maths Club website. Other stuff that I want to advertise in this space, I'm going to advertise the open days. So if you like listening to maths talks, and if you want to talk about colleges and things like that, and admission stuff, then you might be interested in our open days, which are happening this Saturday and next Saturday on the website. I'll put a link in the description, but I think you can find them by looking for Oxford Maths Open Days. There are Maths Department Open Days, where we'll be doing lots of maths. Vicky, is there anything you want to mention or advertise?
Oh, shall I tell you I wrote a book?
You wrote a book?
I wrote a book. It's got a polar bear on the front. I shouldn't cover the polar bear. There we go. I wrote a book.
It's called Why Study Maths. It's got a polar bear on the front. I think that's what we need to say about the book. Lots of people want the cat on the screen. I don't think the cat doesn't go on the screen, does it?
No, she's just walked off. She's sulking.
Fair. Okay, right. We'll at the end of the live stream. I'm really bad at ending these. I'm really bad at doing the wrap up and stop and remembering to turn everything off. They know that. They've seen this before.
Thanks for inviting me, James. It was really fun.
Thanks for coming along, Vicky. It's been great fun. Thanks for teaching us some number theory and Euclid's algorithm. We'll be back for another episode of the Oxford Online Maths Club in 167 hours. I'll see you then. Have a nice evening. Bye. And then awkwardly I have to click the button and we're good.